Hello again students. In this video we are going to derive the electric field due to an infinitely long straight uniformly charged conductor. Well, the title is as long as this wire is. Alright, so let's start. What we have here is a very long straight wire, infinitely long actually, right? So it has no ends. Obviously you can't make such a wire, right? But for practical purposes, we could say that this wire is very long and straight. Okay. Not only that, it is uniformly charged. Okay. That means there is charge at each point of this wire, right? So this is an example of a linear charge distribution, right? I hope you remember that there are three kinds of charge distributions, and this is one of them, right? Linear charge distribution, where charge is distributed everywhere on this wire. Not only that, it is uniform, right? So first of all, I could say that its linear charge density, of this wire, right? Okay, that's lambda, and because it is uniform, it does not depend on the position. So I could just say that lambda is equal to whatever the total charge is on this wire, right, divided by the total length. Okay, whatever that is, right? I know this is very large, this is infinite, so total charge is also huge, right? So here it's not possible to find out the electric field due to each and every point, right? So we'll have to use a trick, and that trick is the Gauss law, right? So this is where Gauss law wins over the Coulomb's law. If you try to find this one by Coulomb's law, it's not possible. It's possible, but it's very, very tough, right? You have to do lots of integrations. But if you do it by Gauss law, it's very straightforward. So let's start. So first of all, what I'm going to do is, let's assume that this is a long straight wire with uniform positive charge over it, right? We consider one point over here. Let's call it anything, maybe P for point. At this point, I want you to think of the electric field due to a small portion that I'm taking here, right? And another small portion that I'm taking here, such that these are symmetrically placed at some distance, right? I don't know what this distance is. Could be anything, doesn't matter, but whatever it is same, right? From this perpendicular line, it's same. Y upwards, Y downwards, simple. So due to this element, due to this small portion and its charge dq, the electric field is going to be in this direction that I've marked as E1. And similarly, due to this portion which is symmetrically located downwards, the electric field is going to be in that direction, right? See, it's away from the positive charge, right? So E1 is in this direction, E2 vector is in that direction, right? But because these are symmetrically placed, the magnitude of electric field E1 and E2 is same. Not only that, their directions are such that both these angles are going to be equal. So finally, the resultant of these two fields is in this direction, that is horizontal direction in this diagram, which means it is perpendicular to the wire, right? So let me write that at any point in space, the electric field due to this wire is in a direction perpendicular to the wire, right? So what I'm saying is, at this point P, the electric field is in right hand direction, okay, and it is perpendicular to the wire, as you can clearly see, right? Let me add a few things. It is in the direction perpendicular to the wire along, okay, never mind. Let's keep it like that. We'll add that later. So at this point, the electric field is in a perpendicular direction, right? Now, if I want to find out what's the value of that electric field, I found the direction, all right, but what's the magnitude? I don't know that yet. So to find that, I'm going to use the Gauss law. I will say that if I make an imaginary cylinder like this, see, I've made an imaginary cylindrical surface or imaginary cylinder. So this is that imaginary cylinder, you are seeing it in red. For that imaginary cylinder, I'm assuming that the radius is r, okay, so that this point P is automatically on that cylinder. So this distance has to be R, right? Okay, and let's say the cylinder has length L. So let's start writing that in words. Okay, so let point P be at perpendicular distance R from the wire. Okay, so we know that this point P is at perpendicular distance R from the wire. So we draw an imaginary cylinder or cylindrical surface. Right? We draw an imaginary cylindrical surface. By the way, such surfaces that you draw, they are called Gaussian surfaces. Right? So you can also write that we draw a Gaussian surface which is cylindrical. Right? So we draw an imaginary cylindrical Gaussian surface with radius R, okay, length L, and axis on the wire. Right? So we are taking the cylinder such that the axis of the cylinder is on the wire exactly. Right? So that automatically means that point P is on that cylinder. Right? So what we'll do now is that for this cylindrical surface, which is a closed surface, we will use the Gauss law and we will find out the electric field at this point. Right? One more thing that I want you to understand is that the electric field at P, or maybe at this point, or maybe at this point, or at this point, or at this point, or this one, is going to be equal in magnitude, right? Not in direction, only the magnitude. Because that all these points that are on the edge of this cylinder or on the surface of the cylinder, they're all at the same distance R. That is, if you would watch it from here, right? Let's say you watch this, you go over there, climb up over there, right, and hang downwards like a bat does and look inside the cylinder, this is what you're going to see. This is the point P, let's say, right, or maybe let's put it here, right. So this is the radius R. Obviously this distance is going to be same, right, and the electric field is going to come out from the wire in, you know, in this fashion, right, in this direction, in radially outwards of, along the radius of this cylinder. So whether you are talking about this point P or some other point, right, anywhere on the curved surface of the cylinder, the electric field will be same in magnitude, not in direction, as you can see, right. Again, this is a positive charge, that's why electric field lines are going up. So what happens is that for any point on the flat surface of the cylinder, for any point on the flat surface, this one, right, what we are seeing is that the electric field is like this, but the normal vector is like this, right. Let me call this N3. Similarly, I could call this one as N1, right. So the same thing happens here or over there, right. So what we are seeing is that for surfaces 1 and 3, which are flat surfaces, the electric field is, let's say, towards right side or radially outwards, left side, behind, anywhere, but it's in this plane, right. But the normal vector is coming down or maybe going up. So, again, if I see it in this view, if I am over here and watching this, then this N1 is going to come towards me, right. The N1 vector comes towards me, but the electric field is going towards the right hand side. So there is an angle 90 degree between them, right. So I can say for surfaces, these two, right. So for flat surfaces, let me just write that. For flat surfaces of cylinder, flux is 0. Why is it 0? Because the electric field and the area vector are perpendicular to each other. So that's done, right. Again, this is exactly like a question that we did earlier. We take this surface and we can split it into 3 parts: flat, curved, and flat. So flat surfaces we are done with, because they are making an angle the normal is making an angle 90 degree, with the electric field, right? But what about the curved surface? Well, come back to this diagram. If you talk about the curved surface, we are finding that the electric field at each point of the curved surface is going to be outwards from that positive charge, right? So this is just like that sphere or circle, right? So the radius and the tangent, they are perpendicular. That's why electric field is in the same direction as the small area vector that you draw at every point. I hope that makes sense to you. At any point, if I draw the electric field and the small area vector, they are going to be in same direction, right? Okay, so for curved surface, angle between E vector and area vector or ds vector is 0 at each point. Okay. Go over through this sentence carefully. For curved surface, at every point what happens is that E vector and ds vector are in same direction, that is angle between E vector and ds vector is 0. Now that means for every point I can put theta's value as 0, right? Not only that, like I said earlier, the magnitude of electric field here or here or here or here is going to be same, magnitude, not direction. Because, now that happens because the situation here, the figure is so symmetrical, right? The wire is located right here at the center, and in every direction its distance r, right? So magnitude is going to be same for every point, right? Magnitude of electric field will be same for every point, but the direction is different. So field is not uniform. Remember this, field is not uniform, but the magnitude is same at all these points on this cylinder's curved surface, right? So for curved surface, angle is 0 between E and ds, and not only that, and the magnitude, mag, magnitude of electric field is equal, right? Okay, so based on these two ideas, we are going to do the integration, right? So let me erase this and we'll do the integration now. So let's see what happens. Flux is equal to, well, integration of E vector dot ds vector, right? So remember, this is for the curved surface, right? So phi is equal to integration of E vector dot ds vector, which is going to be E into ds into cos 0, right? Like I said, angle between E and ds is 0 at every point. Not only that, the magnitude of electric field is same at all points. So I can put the electric field outside of the bracket, right? I don't know the value of the electric field. That's why we are doing this calculation, right? We want to find out what's the value or what's the electric field vector, right? So cos 0 is 1. So this is what you are left with, right? Integration ds. Integration ds means addition of all those small surface areas that you are going to take on this curved surface. Mind well, on this curved surface, not on the flat surfaces, right? We are already done for the flat surfaces. Read this sentence. So what this means is integration ds gives you addition of the surface area for the curved surface. So that is nothing but surface area of the cylinder. It is going to be 2 pi Rn, right? Okay, right? So now this flux is the flux for the curved surface, right? But because other surfaces have 0 flux, I can write therefore net flux for the cylinder or cylindrical surface is E into 2 pi RL plus 0 plus 0. Why am I adding those zeros? Curved surface, the flux is E into 2 pi RL. for the flat surface number 1, it's 0. For the flat surface number 3 is 0. So is equal to, now this is net flux or total flux for the cylindrical surface, that is Gaussian surface. So this I can write to be sigma q enclosed divided by epsilon 0, because I'm using the Gauss law. Okay, right? So that means on the left hand side we have found the electric flux using the basic definition of flux, which is E vector dot S vector, right? Very basic. By that we found these 3 fluxes, right? We get E into 2 pi r L, we get 0 and 0 for the flat surfaces. And now on the right hand side, we have used the Gauss law, right? Because this total flux through the cylinder should be equal to sigma q enclosed divided by epsilon 0. So now E into 2 pi r L is equal to how much charge is enclosed inside this cylinder, right? How much charge is enclosed inside the cylinder. To make it clear once again, let me just draw a new diagram over here. What we have is, we have some cylinder, it has some length L, and there is a wire on its axis like this, right? So how much charge is inside this cylinder? So we should take the charge between these 2 points, right? Between the 2 ends, right? So do you realize that it's going to be lambda into L, right? Why so? Because charge enclosed is the charge held in this portion, right? Its linear charge density is lambda, and the charge we have to find is going to be lambda into L, because definition of lambda is charge upon length. So charge Q divided by the length L, right? Of this portion only, right? Not of the whole wire. We are only talking about charge in this portion between these 2. So we are only taking the length of that portion, right? So Q is going to be lambda L, that's the charge inside it, divided by epsilon 0. So finally, we get E is equal to, well, L is cancelled, we get E is equal to lambda by 2 pi r epsilon 0. That is the magnitude of the electric field at a distance r from this long, straight, uniformly charged wire, right? Again, this is the magnitude, right? So to sum it up, what we did was, we took a cylindrical Gaussian surface, right, around this wire, right? So that this wire is on the axis. The radius of that cylinder is r, the length is L, right? We know that the electric field is in a perpendicular direction to the wire, right? So when we talk about the flux for the flat surface here, it's 0, right? Because area vector goes up like that and the electric field is in that direction, so the angle between these 2 is 90. Just like that, over here the electric field is in that direction and the area vector goes downwards like this, so the angle between these 2 is 90 once again, right? For the curved surface, we see that at every point the electric field is going to be in radial direction or going outwards from this cylinder because of the symmetry. So the angle is 0 between E and ds at every point. So that's why we can do the calculation easily. We can put cos 0 here. Not only that, the electric field magnitude is same due to symmetry. So I can take E outside of the integration and we get flux for the curved surface is E into 2 pi r L, and that's actually the total flux. So that is equal to sigma q upon epsilon 0. So we get this expression of electric field, right? Now there's one thing missing here, and that is writing the direction. This is the magnitude of electric field at a distance r from that wire. But what about direction? Well, have a look at this diagram. Like I said, electric field is going out in every direction, out from the wire. So this direction is called radial, okay, right? So we are going to say that in vector form, we can write electric field vector due to this long straight uniformly charged wire as lambda upon 2 pi r epsilon 0. And in what direction? In the radially outwards direction. That's why r hat, right? It's important to know what are the terms here. lambda is nothing but the linear charge density of the wire. And let me just box this one out so you would be able to remember it. Okay, so linear charge density of wire, R is the perpendicular distance of the point from the wire, right? So wherever you want to find the electric field, its distance from the wire, perpendicular distance from the wire, that is R. Epsilon 0, I am sure you know what it is. R hat is indicating that the electric field is in radial direction. Okay, if lambda is positive, that is the wire is positively charged, the electric field will be going outwards radially. If lambda is negative, the wire is negatively charged and the electric field lines will be coming in, that is radially inwards. Alright, so that's the derivation of the electric field due to uniformly charged long straight infinite wire. Okay.